The story of the Republic's P-47 Thunderbolt begins not merely as the tale of a machine, but as a triumph of industrial power and engineering philosophy. In the middle of the Second World War, when the skies over Europe were ruled by fierce dogfights and desperate innovation, a group of German engineers came across a downed American aircraft unlike anything they had ever encountered before. To them, it seemed impossibly large, almost excessive, a flying fortress of a fighter built around a heart that roared with more than 2,000 horsepower. That heart was the Pratt Whitney R-2800 Double Wasp, a radial engine that symbolized the enormous industrial and technological capacity of the United States. When those German engineers dismantled that captured engine, turning over its intricate components and studying its secrets, they realized something both humbling and frightening. They could not match it. To understand why that realization mattered so much, one has to remember what the air war had become by the early 1940s. Aircraft engines were no longer mere mechanical devices. They were the lifeblood of entire nations' war efforts. Power meant altitude. Power meant speed. Power meant range and survivability, and the ability to bring the fight to the enemy's heartland. The P-47 Thunderbolt was the physical embodiment of that philosophy. Designed initially as an interceptor, it evolved into a fighter bomber, a ground attack monster capable of absorbing tremendous damage and still returning home. Its R-2800 engine wasn't just powerful, it was reliable, mass-produced, and perfectly tuned for the brutal realities of war. When a P-47 was brought down behind enemy lines, accounts vary whether it was crash-landed, forced down, or captured more or less intact, it became a prize. German intelligence immediately transported it to an evaluation center, most likely Rechlin or one of the Luftwaffe's test facilities. Here, engineers and mechanics used to working on Daimler-Benz and Junkers engines gathered around the American radial with a mix of professional curiosity and incredulity. To their eyes, it was massive, far larger than the compact inline engines that powered the Messerschmitt Bf 109 or Focke-Wulf 190. Yet despite its size, they could not ignore what the Allied reports had already hinted at. The P-47 climbed well, dived faster than almost anything else, and its engine rarely failed. As the German team began their examination, they started by cataloging the engine's dimensions and layout. 14 cylinders arranged in 2 rows of 7, air-cooled, each with meticulously machined fins and high-grade alloy construction. The casting and forging quality stood out immediately. German production had always valued precision, but wartime shortages had taken their toll. The R-2800's metalwork, particularly the aluminum alloys used for the cylinder heads and crankcase, seemed of astonishing uniformity. Its tolerances were tight even by peacetime standards. The engineers quickly realized that these engines were not just handmade masterpieces, they were produced by the thousands, each one nearly identical. They were impressed, but they were also puzzled. How could an engine so big, so heavy, power a fighter so effectively? The P-47 was not sleek, it was not elegant. To the European eye, conditioned to admire aerodynamic minimalism and refined balance, the Thunderbolt looked like brute force given wings. But when they looked closer, they began to see the brilliance in its design. The large radial engine gave it not only power, but resilience. It could take hits to cylinders and still run. It could operate at high altitudes thanks to an ingenious turbo-supercharging system that made full use of the engine's potential. The Germans had used superchargers in many of their aircraft, but the American system was on another level. The P-47's turbo-supercharger, positioned in the rear fuselage, compressed exhaust gases using a turbine and routed the pressurized air forward through a series of ducts and intercoolers. It was complex and bulky, but it allowed the engine to maintain full power even above 25,000 feet. This gave American pilots a crucial advantage, particularly in bomber escort missions over Europe, where thin air robbed other engines of performance. As the German engineers traced the lines and valves, they marveled at the scale of the integration. To replicate such a system, they would have needed not only advanced materials, but also vast industrial coordination, the kind that only a nation with near-limitless production capacity could muster. When they turned to the internal components, the surprises continued. The pistons were lightweight but incredibly strong. The crankshaft showed almost no wear, even after considerable flight time. Bearings and lubrication systems were meticulously designed to handle immense stress. Everything about the engine spoke of a philosophy utterly different from their own. German engineering had traditionally emphasized refinement and efficiency, achieving maximum performance with minimal waste. American engineering, by contrast, seemed to revel in abundance. If one component could be made stronger, heavier, or more redundant, it was. It was a philosophy born not of carelessness, but of confidence in material resources. As the Germans studied the R-2800, they compared it mentally to their own power plants. The Daimler-Benz DB605, for instance, was an inline liquid-cooled V12 that produced around 1,475 horsepower in its early versions, and even the later models rarely exceeded 1,800 horsepower. The Junkers Jumo 213, which powered advanced aircraft like the FW-190D, could reach roughly 2,000 horsepower under optimal conditions, but it was temperamental and difficult to produce in quantity. The Americans, however, were churning out R-2800s by the tens of thousands, fitting them into not only the P-47 but also the F-6F Hellcat, the F-4U Corsair, and later models of the B-26 and A-26. For the Germans, who struggled to keep their factories supplied with basic alloys and fuel, this level of standardization was staggering. They noted how the Americans had mastered not only metallurgy but also logistics. Each bolt, gasket, and bearing seemed to be produced with consistency across plants thousands of miles apart. The Germans, by this stage of the war, were fighting to maintain quality control amid bombing raids, forced labor, and resource shortages. Even if they could copy the design, reproducing it at scale was nearly impossible. One of the engineers reportedly remarked that the Americans had built engines the way Germany built artillery, industrialized, repeatable, and unstoppable. There was also the matter of reliability. The R-2800 was famous for its ability to take punishment. Pilots often returned from missions with engines peppered by flak or running on reduced power, yet they survived. The Germans' own high-performance engines, especially the advanced liquid-cooled designs, were far more fragile. Overheating, oil leaks, and fuel line failures were common under battlefield conditions. The P-47's radial, on the other hand, could keep turning even when damaged, its air cooling system eliminating many of the vulnerabilities that plagued inline engines. As they ran calculations and examined each component, the German engineers began to appreciate the hidden sophistication of the American machine. This was not merely brute force, it was systems engineering on an industrial scale. Every element of the Thunderbolt's design, from its engine to its supercharger to its airframe, worked together toward a single purpose: durability and sustained power. It was an aircraft built not for theoretical perfection but for practical supremacy in the chaotic conditions of war. And so, piece by piece, the realization set in. It was not that they lacked intelligence or creativity. They lacked capacity. They could design elegant engines, but they could not mass-produce something so powerful, so consistent, and so forgiving. The R-2800 represented the full might of an industrial democracy geared entirely toward victory. It was the product of vast supply chains, plentiful resources, and an engineering culture that prioritized function over form. To the German engineers, accustomed to scarcity and improvisation, it was like examining an artifact from another world. By the time they finished their analysis, one conclusion was inescapable. They could not match it, not in design, not in production, not in reliability. They could build faster prototypes, they could innovate with jets and rockets, but they could not rival this kind of dependable mechanical excellence. The captured P-47 had become more than just an intelligence trophy. It was a symbol of the technological mountain they were now trying to climb from halfway up the slope. In the days that followed, the German engineers conducted increasingly detailed analyses. They measured compression ratios, inspected valve timing, and even conducted partial bench tests using improvised setups. What struck them again and again was how effortlessly the American engine seemed to manage extreme loads. At full throttle, the R-2800 could deliver consistent power for long durations without overheating or exhibiting the slightest mechanical strain. This was partly due to its sophisticated cooling fin geometry and airflow management. Each fin, each duct had been carefully shaped through extensive wind tunnel and thermal testing. The Germans realized that behind this machine was not just a factory, but an entire research ecosystem. Scientists, metallurgists, and engineers all working in synchronized harmony. One of the engineers reportedly commented that the R-2800 was overbuilt by German standards. Every part appeared thicker, more reinforced, designed to endure abuse rather than to save weight. Yet this wastefulness was deceptive. It was exactly what made the engine resilient. In German aircraft, shaving off a few kilograms was often treated as a mark of excellence. The P-47's designers, however, seemed to have decided that if more metal made a part last longer or survive battle damage, it was worth the extra weight. The result was a fighter that could dive at over 500 miles per hour without its engine tearing itself apart. The Germans, whose engines often required strict limits on overspeeding and temperature, could only marvel at that. When they examined the supercharging system in depth, their astonishment deepened. The P-47's turbo supercharger was, by itself, an engineering marvel. While German engines used mechanical superchargers driven directly by the crankshaft, the American system utilized exhaust-driven turbines to compress intake air. It was a technology the Germans understood in principle. They had experimented with turbocharging in the 1930s, but they never implemented it on a large scale in fighters. The reasons were simple. The materials required for turbine blades that could withstand high heat and stress were scarce, and the manufacturing processes were complex. The Americans had solved both problems through advanced metallurgy and mass production techniques. As they disassembled the turbine assembly, the German engineers noticed the use of exotic alloys, nickel, chromium, and cobalt-based materials designed to endure temperatures approaching 1700 degrees Fahrenheit. These metals were precisely the ones that Germany lacked. With limited access to strategic materials and with blockades cutting off imports, the Luftwaffe had been forced to make do with substitutes that degraded more quickly. The Americans, by contrast, could afford to use the best. To the Germans, that was both infuriating and enlightening. It was proof that technological superiority was not just a matter of design, it was a matter of resources and logistics. When they examined the turbo system's controls, the complexity was staggering. Automatic wastegates, pressure regulators, and manifold sensors ensured the pilot could concentrate on flying rather than constantly managing the engine's breathing. In German aircraft, pilots were trained to manually adjust mixture, boost, and propeller pitch. It demanded skill and constant vigilance. The P-47's automation was a revelation. It meant that even average pilots could extract near-optimal performance. In war, that kind of accessibility mattered enormously. The Germans recognized this, and some even admired it, though others saw it as emblematic of a machine-over-man philosophy they distrusted. As their study progressed, a quiet sense of dread crept into the analysis reports. These weren't mere mechanical differences. They were reflections of entire national mindsets. German engineers had long prided themselves on precision craftsmanship, on the notion that one brilliant designer or a handful of master mechanics could produce world-class machines. The Americans, on the other hand, had industrialized genius. They had taken innovation and made it repeatable. That was perhaps the most humbling revelation of all. A parallel examination was conducted on the P-47's airframe, and it reinforced the same conclusion. Everything was built with redundancy and ruggedness in mind. Control cables were doubled, armor plating was extensive, and hydraulic systems were shielded from battle damage. The Thunderbolt could lose cylinders, oil pressure, or even a supercharger and still limp home. When the Germans compared this to the fragility of their own high-performance fighters, it was an uncomfortable comparison. A single coolant leak could doom a Bf-1 design. A small puncture could cause catastrophic overheating. The Americans had traded elegance for endurance, and endurance was winning the war. Meanwhile, word of the captured aircraft's examination reached higher echelons within the Luftwaffe. Reports summarized the findings: extraordinary reliability, unmatched mass production quality, and exceptional altitude performance. One internal memorandum is said to have remarked that while German jet programs represented the future, the Americans had already achieved perfection in piston engine warfare. That was no exaggeration. At high altitudes, P-47s were escorting bombers deep into the Reich, their engines humming smoothly while Messerschmitts struggled for power. In one demonstration, the engineers attempted to test the P-47's engine in simulated high-altitude conditions. They lacked the facilities to fully replicate the supercharger's performance, but even in basic testing, they noted consistent boost pressure far beyond what their own engines could maintain. The data confirmed what Luftwaffe pilots had been reporting for months. The P-47 seemed unstoppable above 25,000 feet. Its engine simply refused to fade, while their own lost breath. Behind the scenes, a few German technicians proposed ideas for replication. Could the R-2800's features be adapted to existing German engines? Could they produce similar metallurgy or copy the supercharger layout? Theoretically, yes, but practically, no. They lacked the alloys, the precision casting methods, and the scale. Wartime Germany's production was already under immense strain. Factories were being bombed, and every hour of labor had to count. Even if they could build one prototype, mass production on American levels was a fantasy. It was around this time that a sense of resignation began to appear in technical reports. The Germans realized that the war was not just a battle of machines, but of systems. The R-2800 was the physical proof that the American system worked. Its industries, its supply chains, its education, its factories. Each rivet and bearing told a story of a society capable of overwhelming consistency. And that, perhaps, was more frightening to them than the engine's raw power. Still, admiration persisted. The German engineers, for all their pride, were scientists and craftsmen at heart. They could not help but respect what they were seeing. Some took notes not just for the immediate war, but for the future. Concepts they would later use in post-war aviation projects, both in Germany and abroad. When the war ended and many of these engineers found themselves working in the United States, France, or the Soviet Union, their experiences examining Allied equipment became invaluable lessons in humility and progress. The R-2800 had set a standard. Its combination of high power, reliability, and manufacturability became the model for post-war piston engines. Even jet designers studied its systems engineering principles, the way every subsystem integrated smoothly into the whole. It wasn't a masterpiece because it was flawless. It was a masterpiece because it was practical. For the men who had first stood around that captured P-47, however, it represented a turning point. They realized that the war they were fighting was already unwinnable on technological terms. No matter how skilled their pilots, no matter how daring their designs, they could not bridge the industrial chasm that separated them from their enemies. The Thunderbolt's engine was the mechanical embodiment of that truth, a roaring, unstoppable symbol of what total mobilization could achieve. Even years later, when those same engineers recalled the experience, their words carried a mix of awe and melancholy. They had seen the future in that engine, and they had understood too late that they were living in the past. When the German engineers reported their findings up the chain of command, the tone of their analysis was almost reverent. They detailed the metallurgy, machining, and systems design with a precision that bordered on admiration, but behind their words lay an unmistakable sense of frustration. The R-2800 was not a product of a single breakthrough that could be copied or stolen. It was the sum of countless incremental advances, each dependent on resources, infrastructure, and production discipline that Germany could not replicate under siege. These engineers' meticulous notes, complete with sketches and measurements, filled binders that would later be discovered by Allied intelligence teams after the war. They reveal a fascinating duality. On one hand, the German pride in recognizing superior craftsmanship, and on the other, a dawning realization of industrial defeat. They had always believed that German science was the envy of the world. Their chemists, physicists, and metallurgists had been leaders for decades. Yet here was a machine that embodied a different kind of genius, one rooted not in laboratory brilliance but in mass application. America's strength lay in its ability to coordinate thousands of minds toward one common objective. The P-47's engine was not designed by a single visionary. It was refined by teams of engineers working in concert, drawing on a manufacturing base that could make thousands of identical parts with microscopic precision. That was something Germany had never achieved on such a scale. As the Germans pored over the cooling system, they saw another example of this holistic thinking. The air-cooling fins, precisely spaced and shaped, ensured optimal heat dissipation even under combat stress. The cowling design created a vacuum effect that pulled air efficiently across the cylinders. They realized that the Americans had perfected the airflow dynamics to such a degree that the engine stayed within safe temperatures even during long climbs or extended bursts of power. The Germans' own radial engines, like the BMW 801, were excellent designs but required constant adjustment and careful maintenance to avoid overheating. The R-2800, by contrast, seemed almost carefree. Its reliability made it ideal for long missions where maintenance was minimal and performance demanded consistency. They also discovered the brilliance of American accessory design. The magnetos, carburetors, pumps, and regulators were arranged for accessibility and ease of maintenance. Each component was modular, designed to be replaced quickly by ground crews rather than repaired in the field. German engines often required skilled mechanics to adjust or repair even minor issues, and spare parts were becoming scarce as the war dragged on. In contrast, American ground crews could service an R-2800 in the open, using standardized tools and replacement parts that fit perfectly every time. This efficiency translated directly into combat readiness. The P-47 spent less time grounded and more time flying missions. The Germans were also intrigued by the electrical and ignition systems. They found redundancy in every critical function. Dual magnetos, twin ignition circuits, and fail-safes ensured that even if one system failed, the engine would keep running. It was over-engineering in the best sense of the word, an intentional design philosophy that valued reliability above all else. The more they studied, the more the German engineers realized how fundamentally different the American approach was. In Germany, aircraft engines were masterpieces, individually calibrated and often requiring delicate tuning. In America, they were products, reliable, repeatable, and built to last through hundreds of flight hours of abuse. When they tested the oil system, they found it similarly advanced. The Americans had adopted a dry sump lubrication system with efficient scavenging pumps that maintained constant oil pressure in all flight attitudes. Even during high-G maneuvers, the R-2800 maintained steady lubrication, preventing the oil starvation that plagued some German designs during dives and tight turns. The system was not just functional, it was elegant in its simplicity. The engineers could not help but respect the practical genius behind it. As they continued their teardown, their discussions grew philosophical. One engineer noted that the R-2800 reflected a kind of industrial democracy. Every component, from the smallest valve spring to the massive crankshaft, was designed to do its job without relying on extraordinary craftsmanship or fine adjustment. It was a machine designed for ordinary workers to build and maintain, not for specialists or artisans. In that sense, it was a mirror of the society that created it, a nation of factories, standardization, and collective effort. Germany's centralized hierarchical structure had produced brilliant inventions, but it could not sustain the level of cooperative mass production that America achieved. There was another element that caught their attention: the quality of the fuel system. American 100-octane fuel, developed through intensive chemical engineering, allowed engines like the R-2800 to run at higher compression ratios and boost pressures without detonation. German fuel was typically lower in octane, often around 87 to 96, and as the war dragged on, shortages forced the use of even poorer substitutes. The engine's power was not just mechanical, it was chemical. With high-octane fuel, the Americans could push the limits of supercharging safely, extracting every bit of energy from each drop. The Germans could not match that without equivalent fuel quality, and by this stage of the war, such resources were impossible to obtain. Perhaps the most sobering discovery came when they examined the manufacturing markings on the parts. Each component bore serial numbers and codes indicating its origin, often from entirely different factories scattered across the United States. Yet every piece fit perfectly. That level of standardization was mind-blowing. It showed that thousands of workers across hundreds of locations were producing interchangeable parts without ever seeing the final assembly. The Germans had nothing comparable. Their production relied heavily on skilled labor and local adjustment. Precision, yes, but not interchangeability. The captured R-2800 was living proof that industrial standardization had reached near perfection in America. Some engineers tried to rationalize their findings. They argued that the Americans had simply taken a brute force approach, throwing material and manpower at the problem. But even that explanation failed to diminish their respect. Brute force, when harnessed intelligently, was a form of genius. The P-47's engine was not elegant in the traditional sense, but it was unstoppable. It embodied the raw power of an industrial empire operating at full throttle. Every rotation of its crankshaft seemed to echo the pulse of a nation that could outproduce its enemies tenfold. In quiet moments after the formal tests were done, some of the engineers speculated about what would happen after the war. If such engines were the standard of American production, what would peace bring? What kind of civilian aircraft, what kind of technology would emerge when the same minds that built these engines turned to peacetime projects? They knew, deep down, that the world would never be the same. The age of small-scale precision was ending, and the age of industrial systems had arrived. Still, they took pride in what they had learned. They recorded every measurement, every alloy composition they could identify, every temperature tolerance they could infer. They were professionals, after all, and their respect for good engineering transcended national boundaries. In a different world, they might have admired the R-2800 as colleagues rather than adversaries. But in 1944, their admiration came with the bitter taste of inevitability. In the final analysis report, one of the senior engineers wrote a sentence that captured the essence of their discovery. It is not possible for us, under current circumstances, to construct an engine of equivalent power and reliability with our existing materials and methods. It was a rare admission of defeat from men who prided themselves on technological superiority. The R-2800 had shown them the limits of their own capabilities and, by extension, the limits of the Reich itself. As the investigation continued, the German engineers broadened their scope beyond the engine itself. They began to see the R-2800 not as an isolated marvel, but as the centerpiece of a larger ecosystem, a web of manufacturing, logistics, and engineering philosophies that all work together. In meetings and reports, they discussed how every American component seemed to exist as part of a grand system. Even the bolts and screws bore markings of consistency, evidence of standardized supply chains. For engineers accustomed to improvising around shortages, this level of uniformity was both astonishing and demoralizing. It revealed that the Americans were fighting a different kind of war, one built on planning, coordination, and endless production capacity. One of the engineers, a man who had previously worked on the BMW 801 project, compared the experience to examining a living organism. "Every part of this engine," he wrote, "functions like an organ in a perfectly evolved creature. Remove one, and another compensates. It does not rely on delicacy, it relies on balance and strength." That analogy stuck. To them, the R-2800 was not merely an engine, it was a symbol of industrial evolution. The turbo-supercharger continued to fascinate them. The Germans had long pursued mechanical perfection, and here they found a triumph of practical engineering. The R-2800's turbocharging system was not elegant in design. It was bulky, sprawling, and used long ductwork that wound through the fuselage. But it worked flawlessly. The system's robustness amazed them. Its heat-resistant materials, automatic regulators, and redundant safety valves allowed the P-47 to operate at altitudes where most other piston engines gasped for air. The Americans had even managed to integrate a complex network of cooling ducts and wastegate controls that adjusted themselves automatically, requiring minimal pilot intervention. When the engineers traced these systems through the fuselage, they marveled at the precision of assembly. The ducts were sealed so tightly that almost no pressure was lost, even after prolonged use. That kind of fit required not just good design, but world-class manufacturing precision on a massive scale. The Germans could achieve such tolerances in prototype workshops, but not across hundreds of factories. This realization reinforced a painful truth. America's advantage was not innovation alone, but the ability to mass-produce innovation. By the time the engineers had completed their teardown, the room was filled with neatly labeled components, hundreds of them, each polished and cataloged. There was reverence in their work, a kind of reluctant awe. They spoke quietly, aware that what they were witnessing represented a level of industrial might that their nation could no longer challenge. Every bolt, every spring was proof that America had achieved something extraordinary. Some of the older engineers recalled the days before the war, when Germany's aircraft industry had led the world. The Daimler-Benz and Junkers engines of the 1930s had been marvels of compact design, admired by pilots everywhere. But the war had changed everything. Scarcity had eroded their advantage. Synthetic fuels, substitute materials, and rushed production had taken their toll. Meanwhile, across the Atlantic, American factories had only grown stronger. The engineers realized that this imbalance had been building long before the first bombs fell. A few among them, driven by curiosity and pride, proposed theoretical improvements. They drafted sketches of hybrid systems, German engines equipped with American-style turbochargers, or radial engines adapted to local designs. On paper, these ideas were intriguing, but everyone knew they were fantasies. The necessary alloys didn't exist in sufficient quantity, and production infrastructure was crumbling under Allied bombing. Even if they could design an equivalent engine, they had no means to build it in numbers that mattered. Still, the engineers took comfort in the intellectual challenge. They analyzed the P-47's performance data, calculating its power-to-weight ratio, specific fuel consumption, and mean time between overhauls. The results were staggering. The R-2800's reliability exceeded any German engine by a wide margin. While most Luftwaffe power plants required frequent overhauls after 100 to 150 flight hours, the American engine could often exceed 300 without major issues. That meant more sorties, more missions, and less downtime, a factor that multiplied the effectiveness of every squadron that used it. They also noted the engine's adaptability. It powered not only the P-47 but a whole family of aircraft. The F-6F Hellcat, F-4U Corsair, and even bombers like the A-26 Invader. This versatility reflected another fundamental strength of American design philosophy. Modularity. The Germans had built engines for specific roles, optimizing each design for a particular aircraft. The Americans had built an engine that could serve multiple roles, changing only accessories and mounts. This flexibility saved enormous time and resources. It also gave American forces a logistical advantage that no amount of tactical brilliance could overcome. As they documented these observations, the German engineers began to see the broader implications. The P-47's success was not just a triumph of engineering, it was a manifestation of strategic foresight. The Americans had designed a machine that fit their war doctrine perfectly. Long-range missions, high-altitude operations, and sustained firepower. It was a weapon made for endurance, for attrition, for the kind of war Germany could not afford to fight. In their quieter moments, some of the engineers discussed the philosophical contrast between their nation's approaches to engineering. The Germans believed in craftsmanship, machines as art perfected through precision and refinement. The Americans believed in systems, machines as tools perfected through iteration and scalability. One approach sought perfection, the other sought reliability. And in war, reliability won. As the war drew closer to its end, the findings from the P-47 examination faded into the background of Germany's collapsing infrastructure. Reports were filed away, laboratories evacuated, and factories dismantled or destroyed. Yet among those who had studied the R-2800, the memory lingered. They had looked into the heart of their enemy's machine and seen not just superior engineering, but a superior system of thought. It was a lesson that would stay with them long after the war was over. After the war, many of these same engineers would find themselves working under new flags. Some were recruited by the Americans under Operation Paperclip. Others joined French or Soviet programs. Wherever they went, their experience with the P-47's engine shaped their understanding of modern engineering. They brought with them a new respect for mass production, standardization, and practicality. The lessons learned from the captured Thunderbolt became part of the foundation for the next generation of aviation technology. In retrospect, the German examination of the P-47's engine was more than a technical investigation. It was a moment of realization that the age of the artisan engineer was over. The new era belonged to the industrial engineer, the systems designer, the organizer of production. The R-2800 represented that shift perfectly. It was not the product of genius alone, but of organization, of a nation that had learned to harness creativity on an industrial scale. And for those German engineers, standing in that hangar, surrounded by the disassembled remains of the Thunderbolt's heart, that realization must have been both awe-inspiring and tragic. They had devoted their lives to mastery of machines, and here, in the wreckage of a captured enemy aircraft, they saw the limits of that mastery. The war had not just been lost on the battlefield, it had been lost in the factories, in the foundries, in the systems that produced engines like the R-2800 by the thousands. In the weeks following their examination, the German engineers were ordered to compile a comprehensive dossier on their findings. The report was to include performance comparisons, mechanical assessments, and potential applications for any insights gained. What emerged was a technical document that read almost like a confession. While the authors maintained professional detachment, the underlying tone was unmistakable. Admiration tinged with resignation. They knew that no matter how meticulously they studied the P-47's engine, they could not reproduce it. Not with the materials they had, not with the factories they possessed, and not under the crushing weight of Allied air raids that turned industrial centers into rubble. They began by summarizing the R-2800 specifications. Its 18-cylinder, twin-row radial configuration, displacing over 45 liters, delivering more than 2,000 horsepower at takeoff. They described its supercharging system, lubrication network, and ignition setup in extraordinary detail. Each section of the report ended with the same conclusion: exceeds German capability under current wartime conditions. It wasn't simply that the Germans lacked the skill, they lacked the ecosystem that made such an engine possible. When they compared the R-2800 to their own designs, the contrasts were stark. The BMW 801, though powerful, was constrained by its reliance on mechanical supercharging and sensitive thermal management. The Daimler-Benz DB605, used in the Messerschmitt Bf 109, was finely engineered but fragile, requiring constant attention and precise cooling. The Junkers Umo 213 approached the R-2800's power levels, yet its complexity and production difficulties limited its availability. The German engineers knew that in theory they could design a radial engine of similar displacement, But without access to high-temperature alloys, precision casting, and abundant fuel supplies, it would never achieve the same results. They also noted that the R-2800's mass production did not degrade its quality. In fact, they were stunned by how consistent the machining was. Measurements taken from multiple components revealed tolerances tighter than many of their own factory-fresh parts. This discovery forced a painful realization. American machine tools were not only more numerous, they were more advanced. German factories had long depended on skilled machinists to hand-finish parts. The Americans had developed automatic lathes, jigs, and gauges that allowed less skilled workers to achieve perfect consistency. It was an inversion of everything the Germans had believed about craftsmanship. As they continued writing, the engineers began to explore the reasons behind these differences. One conclusion stood out. The American approach to engineering emphasized process over perfection. Instead of building each engine as a unique creation, the Americans built systems to ensure every engine met the same standard. That philosophy extended beyond design. It permeated their training programs, their supply chains, and even their testing protocols. German engineers realized that America's true weapon was not any single technology, but its mastery of process. The report also commented on the engine's maintainability. The R-2800 was built to be serviced quickly. Oil filters, spark plugs, and even major components like magnetos could be replaced in minutes. Everything was accessible, labeled, and standardized. German aircraft, by contrast, often required disassembly to reach critical systems. That difference meant that American ground crews could keep aircraft operational at a rate the Luftwaffe could never match. In war, that kind of uptime translated directly into dominance in the skies. Another section of the report focused on fuel efficiency and thermal performance. The Germans were impressed by how effectively the R-2800 managed heat despite its power output. Its oil coolers, fin geometry, and ducting created a near-perfect balance between temperature control and aerodynamic drag. They observed that even in high-temperature tests, the engine showed minimal oil breakdown and no significant loss of compression. That kind of endurance, they concluded, could only be achieved through superior metallurgical quality and careful testing. It was engineering confidence on a scale they had never encountered. As the engineers wrote, Allied bombers roared overhead almost daily. The irony was not lost on them. The very aircraft destroying their factories were powered by the same kind of engines they were now studying. Some of them wondered if the reports they were compiling would even reach Berlin before the next bombing raid reduced their offices to ash. Still, they worked meticulously. The pursuit of knowledge was their only refuge in a collapsing world. When they turned their attention to the manufacturing methods, they uncovered perhaps the most telling difference of all. The Americans had developed production lines so efficient that engines could be built and tested in hours rather than days. Automated assembly jigs, precision gauges, and conveyor systems ensured that each part fit seamlessly with the next. In Germany, engines were still largely assembled by hand. Skilled craftsmen adjusted tolerances manually, a process that was both time-consuming and error-prone. Under normal circumstances, this approach might have produced works of art. But in total war, art could not compete with efficiency. One anecdote from the engineers' notes captures their frustration perfectly. During disassembly, they examined a bearing that showed almost no wear after dozens of flight hours. Its surface finish was mirror smooth, the result of precision grinding techniques unknown in Germany at the time. When they attempted to replicate it using local methods, the bearing failed under load. They concluded that the Americans had access to specialized machine tools capable of finishing parts to microscopic smoothness, tools that Germany simply could not produce anymore due to shortages and bomb damage. The engineers also remarked on the engine's modular design. Major components could be replaced individually, allowing damaged engines to be rebuilt quickly in the field. In Germany, engines were often treated as monolithic units. If one part failed, the entire engine required factory overhaul. This difference meant that American squadrons could repair and return aircraft to service within days, while the Luftwaffe struggled to maintain even minimal readiness. There was a moment of somber reflection when they realized how this philosophy reflected the nations themselves. The American system allowed for failure and recovery. The German system demanded perfection and punished deviation. In the R-2800, they saw a machine built to survive imperfection, to keep working even when damaged, dirty, or mistreated. That resilience mirrored the American war effort, flexible, adaptive, and ultimately indomitable. When the report was complete, it spanned hundreds of pages filled with schematics, measurements, and technical commentary. The engineers delivered it to their superiors with the professionalism expected of them, though privately many knew it would change nothing. Germany was no longer in a position to implement the lessons learned. Still, they took a certain pride in the thoroughness of their work. If nothing else, they had preserved a record of one of the greatest mechanical achievements of the war. In later years, historians would find fragments of those reports in archives and bunkers, some damaged, others carefully preserved. They offered a rare glimpse into the mind of a defeated nation grappling with the scale of its opponent's superiority. Reading them today, one can almost hear the mixture of respect and despair in their tone. These were not merely technical notes. They were the reflections of men who had glimpsed the future and realized they could not catch it. As the engineers concluded their report, the mood within the testing facility was somber but thoughtful. The P-47's R-2800 engine had given them a rare opportunity to look into the soul of their adversary's industrial genius. To those men, steeped in the traditions of European precision and scientific elegance, it was a revelation. They began to realize that the American approach to technology was not about creating the most refined or artistic solution. It was about creating the most effective one. The more they studied the engine, the more they understood that its true power came not merely from horsepower figures but from philosophy, a mindset that valued practicality over perfection and endurance over delicacy. In discussions after hours, some of the younger engineers spoke with almost childlike fascination. "It's as if they designed this thing to be abused," one said. "They built it knowing it would be mistreated, overheated, pushed to its limits, and they made sure it would still run." That observation captured the essence of what separated the American design from their own. German engines demanded care. They were thoroughbreds, fast and temperamental. The R-2800 was a draft horse, unstoppable, tireless, and forgiving. And in a war of attrition, the draft horse was the better bet. The team's senior engineer, a man named Kurt Brenner, tried to put their findings into perspective during a final debriefing. "This engine," he told his colleagues, "represents more than technology. It represents a civilization that can build something like this, not as an exception, but as routine. They can do it again and again, perfectly, because their system allows it. They don't need miracles. They have factories." His words hung in the air. Everyone in that room understood what he meant. Germany had brilliance, but America had momentum. Brenner went on to compare the R-2800's mass production consistency to what they saw in their own factories. "We depend on craftsmen," he said. "They depend on process. We value the man who can fix what is wrong. They value the man who makes it impossible for things to go wrong." That distinction struck deeply. It wasn't just a technical difference, it was cultural. American engineers had designed the engine to minimize the need for intervention. It was built to succeed in the hands of ordinary mechanics under extraordinary conditions. The engineers also reflected on how this philosophy extended to the aircraft itself. The P-47's airframe was enormous by fighter standards, with thick wings and a rugged fuselage. To German eyes, it looked clumsy. But in combination with the R-2800, it became a tank of the sky. The Thunderbolt could take hits that would shred other fighters and still return home. The engine's radial design contributed to this survivability. Unlike the liquid-cooled engines in German aircraft, it had no vulnerable coolant system to rupture. A bullet could puncture a cylinder, and the pilot might lose some power, but the engine would keep turning. That resilience saved countless American pilots and made the P-47 a legend. When they compared it to their own fighters, the difference was glaring. The Messerschmitt Bf 109 was nimble and deadly but fragile. A few hits in the cooling system or the oil lines could bring it down. The Focke-Wulf 190, their most durable fighter, still lacked the P-47's sheer endurance. The German engineers recognized that while their aircraft excelled in short tactical engagements, the Americans had built machines for a strategic war. Long missions, high altitudes, and sustained power. That was the kind of war Germany could never truly win. One of the engineers, a metallurgist named Adler, spent days analyzing the alloys used in the engine's pistons and turbine blades. What he found impressed him beyond words. The Americans had mastered nickel-based superalloys capable of surviving extreme temperatures without deformation. These materials were rare and expensive, requiring precise chemical control and vast production facilities. Germany, crippled by resource shortages, simply couldn't match that level of refinement. "We are fighting a war of iron," Adler remarked in his notes, and they are fighting a war of chemistry. He meant that America's scientific strength extended beyond mechanical design. It included the chemical industries that made high-octane fuel, heat-resistant metals, and advanced lubricants possible. The deeper they looked, the more interconnected everything seemed. The R-2800 was not an isolated triumph, but the result of a chain of innovations stretching from metallurgy to logistics. The turbo supercharger relied on nickel-chromium alloys. Those alloys depended on mining and refining operations in places like Canada and the Caribbean. The oil system worked flawlessly because America's petroleum industry could produce synthetic lubricants tailored to specific engine needs. Even the spark plugs were superior, mass-produced with ceramic insulators that rarely cracked under pressure. The Germans began to see that every part of the American war machine was supported by an industrial ecosystem that dwarfed their own. Brenner noted in one internal memo that the engine symbolized a total system victory. He explained that even if German engineers could design an equivalent engine, they could never build it fast enough, nor could they maintain it in the field. Our advantage in knowledge, he wrote, is irrelevant without the means to apply it. It was a bitter admission. For years, German science had led the world in theory and innovation, but now theory had been outmatched by scale. In one of the final stages of testing, the team decided to run the R-2800 at maximum simulated power using improvised equipment. Despite their limited resources, they managed to get it running under load for several minutes. The roar filled the hangar, shaking the walls. The sound was deep, powerful, and steady, a mechanical heartbeat. When they shut it down, the engine showed almost no signs of strain. Its temperatures remained stable, and there was no evidence of oil leakage or bearing wear. The Germans stood silently around it, the smell of hot metal and oil heavy in the air. In that moment, they weren't thinking about nations or ideologies. They were simply witnessing mechanical perfection. One young engineer who had spent most of his career working on underpowered trainer aircraft stared at the still spinning propeller hub and muttered, "This is how you win wars." No one disagreed. Afterward, Brenner wrote a final addendum to the report. In it, he summarized everything they had learned, but he also reflected personally on what it meant. He wrote, "We have always believed that victory belonged to the nation with the greatest minds. But this engine proves that victory belongs to the nation that can turn its minds into machines, and its machines into thousands of copies without flaw." His words captured the quiet transformation that the examination had caused within all of them. They had come expecting to find clever tricks or hidden secrets. Instead, they found discipline, order, and the immense power of collective engineering. As the report was dispatched to Berlin, Allied bombers once again filled the skies. The air raid sirens wailed, and the engineers took shelter, clutching the very papers that described the engines driving those bombers. Some of them would not survive the next few months. Yet their work would endure, in captured documents, in post-war interviews, and in the memories of those who lived to see peace return. In the end, the examination of the P-47's engine was not merely an act of espionage or technical study, it was an encounter with the future. It revealed to the Germans that the age of individual brilliance was being replaced by the age of organized strength. The R-2800 was more than a mechanical masterpiece. It was proof that America had industrialized ingenuity itself. By the time the final phase of the examination concluded, the atmosphere among the German engineers had transformed from technical curiosity into quiet reflection. They had taken apart every bolt, every cylinder head, every manifold of the Pratt Whitney R-2800 double wasp. Each discovery only reinforced the same conclusion. The Americans had achieved a level of engineering balance that transcended traditional boundaries. The R-2800 wasn't simply more powerful, it was complete. Every subsystem, from the oil-scavenging pumps to the magneto wiring, had been designed to complement every other. It was a perfect blend of practicality, efficiency, and brute strength. They realized that this balance was no accident. It was the result of a production philosophy honed through decades of industrial development. In the United States, design and manufacturing evolved together. Engineers didn't just draft ideas, they collaborated directly with machinists and production planners. Factories and design offices worked as one entity. The Germans, by contrast, had maintained rigid hierarchies. Designers designed, workers built, and communication between the two was limited. The R-2800 embodied the opposite of that divide. It was the product of total integration, As the team finalized their documentation, they began to consider the broader implications. What did this mean for Germany's future? If the Americans could produce engines like this in peacetime, what would they achieve when the war was over? The engineers speculated that such technology would lead to new kinds of aircraft, perhaps even civilian transports capable of unprecedented range and reliability. They were not wrong. Within a few years, the R-2800's descendants would power airliners, cargo planes, and even the early Cold War fighters that patrolled the skies over a divided Europe. But in 1944, those thoughts were tinged with sorrow. The engineers were patriots. They had dedicated their lives to advancing German aviation. To admit that their enemy had surpassed them was not easy. Yet professional respect overcame pride. As one of them wrote in his notebook, "It is impossible not to admire what we see here. This machine represents everything that makes engineering noble: discipline, logic, and purpose." That sentiment, written in neat pencil on a stained page, captured the mood of the entire team. In their more analytical moments, they attempted to trace the specific advantages that gave the R-2800 its edge. They noted its exceptional power-to-weight ratio, which allowed it to deliver massive thrust without compromising reliability. They studied the airflow through the cooling fins and realized how carefully the Americans had balanced aerodynamics with heat management. Even the exhaust system, which seemed crude at first glance, was optimized for energy efficiency, diverting just enough gases to drive the turbocharger while minimizing back pressure. There were no wasted parts, no overcomplications. The design exuded confidence. When they compared it to German engines like the BMW 801, they were struck by how differently each side approached the same problem. The BMW 801 was elegant and compact, a masterpiece of packaging, but it demanded precise control and constant maintenance. Its mechanical supercharger robbed power and increased stress on the engine at high altitudes. The R-2800's turbo system, though bulky, allowed for consistent performance across a wide range of altitudes without punishing the engine. It was, in short, forgiving. And in war, forgiving machinery saves lives. One of the most surprising findings came from the engine's testing logs, recovered from the cockpit of the captured P-47. The Americans had recorded every maintenance interval, every oil change, every repair with meticulous detail. The logs showed how long the engine had been running before capture, and the numbers stunned the Germans. It had exceeded 250 flight hours without major overhaul, far beyond what they considered possible for such a high-output machine. They realized that American pilots were flying engines that performed at their best, day after day, with minimal mechanical anxiety. It gave them confidence in combat, a psychological advantage as valuable as any technical one. Some of the younger engineers questioned whether such an approach could ever have been achieved in Germany. The answer, given quietly by Brenner, was simple: not without peace, not without abundance. He explained that Germany's obsession with maximizing performance from minimal resources had forced it into a corner. Every gram of material, every drop of fuel, every minute of labor had to be justified. The Americans, with their vast supply chains and endless oil, could afford to design for reliability first and efficiency second. The irony was that their wasteful abundance had led to a kind of purity, the freedom to perfect what others could only imitate. The engineers began to discuss what might have been different if Germany had pursued a similar philosophy before the war. Could they have built something comparable to the R-2800? Perhaps, in theory. The pre-war Junkers Jumo 222 program had aimed to create a multi-bank engine of immense power, but its complexity doomed it. The German system favored experimental brilliance over industrial stability. The Americans, by contrast, avoided exotic designs in favor of proven concepts refined through iteration. The double wasp had not appeared suddenly. It was the result of years of steady evolution, each version building on lessons from the last. In the evenings, as the men packed up their tools and notes, conversations often drifted to the pilots who had flown the P-47. They imagined what it must have felt like to sit behind that engine, to feel its vibrations as it lifted the heavy fighter into the thin air above Europe. They knew the Thunderbolt's reputation: pilots who had returned home after taking catastrophic damage, engines running on half their cylinders, yet still pulling them to safety. Those stories had once sounded like propaganda. Now they understood they were true. The examination changed them in ways none of them expected. It humbled them, yes, but it also reignited their respect for engineering as a universal craft. War had turned invention into a weapon, but in those quiet hangars, stripped of ideology, they were simply men of science studying a masterpiece. They were reminded of why they had become engineers in the first place. Not for glory, not for conquest, but for the pursuit of excellence. As the project came to an end, Brenner stood with his team before the reassembled R-2800. The engine, though no longer functional, looked almost regal under the flickering lights. "We will never forget this," he said quietly. "One day, when the world is no longer burning, engines like this will take men across oceans instead of into battle." There was silence, then slow nods. Even in defeat, they could imagine a better world built on the lessons this machine had taught them. That night, as Allied bombers thundered overhead once more, shaking the windows of the test hall, Brenner looked up and smiled bitterly. Somewhere in the sky above, another R-2800 was roaring, unstoppable, untouchable, and victorious. The following days brought new orders. The engineers were to crate up the disassembled R-2800 components and transfer them to another facility for long-term study. As they worked, there was an almost ritual quality to their movements. Each cylinder head, each section of tubing, was handled with care and reverence. It was not the reverence of soldiers handling a captured weapon. It was the quiet respect of craftsmen who'd encountered a masterpiece. They packed the parts in straw and cloth, sealing them in wooden boxes marked with technical codes that, to them, carried the weight of a final farewell. When the trucks arrived to carry the crates away, the men stood by in silence, watching the engines that had fascinated and humbled them vanish down the road toward an uncertain future. None of them said it aloud, but they all understood the symbolism. The departing crates represented the last chapter of an era, the closing moment of Germany's confidence in its mechanical supremacy. The R-2800 had revealed that the future belonged not to the nation with the finest minds, but to the one with the most efficient system. In the weeks that followed, Brenner and his team were reassigned. Some were sent to other facilities to work on emergency jet programs, others to attempt further refinements on existing piston engines. Yet none could shake what they had learned. The jets, though innovative, were rushed and fragile. The engines failed as often as they flew. Compared to the steady, thunderous reliability of the American radial, these desperate last-minute creations felt like fragile experiments. They were brilliant, yes, but brittle. Too little, too late. Brenner himself was reassigned to a research division that tested new alloys for turbine blades. He threw himself into the work, trying to apply lessons from the R-2800's durability. But deep down, he knew the outcome. They lacked the raw materials and the time to perfect anything. Each day he heard the distant rumble of bombers, the same kind powered by the engine he had once studied. It was a cruel irony that the very sound that shook his laboratory walls was also a mechanical symphony he had come to admire. Meanwhile, news spread quietly through Germany's engineering circles. Rumors circulated about the captured P-47 and its incredible power plant. Engineers whispered about the engine that could run forever, the supercharger that made altitude irrelevant, the metals that never melted. It became something of a legend, half envy, half inspiration. To some, it was proof of America's excess. To others, it was proof of what discipline and organization could achieve. For Brenner's team, it was both a lesson and a mirror, showing them what they had lacked all along. As 1945 approached and the war's outcome became inevitable, many of those same engineers found themselves wondering what would happen when the fighting ended. Would they ever be allowed to build again, to create for the sake of creation rather than destruction? Some clung to the idea that the future might still need them. In the ruins of Europe, machines would have to be rebuilt, industries reborn, and perhaps, just perhaps, the lessons learned from that magnificent American engine would guide them toward something new. When Germany finally surrendered, the records of the P-47 examination were scattered. Some were captured by Allied intelligence teams, others burned in frantic evacuations. A few of Brenner's handwritten notes survived, preserved by colleagues who smuggled them out in briefcases. In post-war interrogations, Allied officers asked German engineers what they thought of American technology. Over and over, the same answer appeared: efficient, reliable, beyond our means. In 1946, Brenner was among those approached by Allied recruitment officers. They offered him a choice: remain in a devastated Germany or work abroad under supervision. He chose to work for a civilian research institute in France, where he found himself once again surrounded by engines. To his quiet astonishment, one of the first he studied was a Pratt Whitney R-2800. this time mounted on a post-war transport aircraft used for reconstruction. When he saw the familiar contours of the cylinders, he felt a rush of recognition, almost affection. He ran his hand across the cowling and smiled faintly. "We meet again," he whispered. It was then that he truly understood how far the world had come. The engine that had once represented an unbeatable enemy was now a tool of peace, ferrying food, medicine, and supplies across a recovering continent. It roared above cities that had once been targets, its power no longer a weapon, but a bridge. Brenner often thought of his wartime colleagues and wondered if they too had found ways to apply what they had learned to rebuilding rather than destroying. For him, the R-2800 became a symbol of redemption. It taught him that engineering, at its core, was not about national pride or military triumph. It was about human progress. Machines like that engine transcended borders and ideologies. They were born from knowledge, discipline, and the universal desire to make something work better than before. When he lectured young engineers after the war, Brenner often told the story of the P-47. He described how he and his team had examined the captured engine, expecting to find secrets of genius, but discovering instead the power of organization and cooperation. He told them, the true secret of that engine was not in its metal, but in its method. His students listened in awe. Many of them were part of a new Europe, determined to rebuild through collaboration rather than conquest. The old divisions were fading, replaced by respect for innovation wherever it came from. Brenner's story became a quiet legend in the engineering community, a reminder that humility and curiosity were as essential to invention as skill and intellect. Years later, when he was an old man, Brenner visited an airfield in England where several preserved World War II aircraft were being restored. Among them was a gleaming Republic P-47 Thunderbolt. Its polished metal reflected the afternoon sun, and its radial engine stood silent, but proud. As the restorers prepared to start it, Brenner stood at a respectful distance, hands folded behind his back. When the starter whined and the R-2800 coughed to life, the ground trembled. The deep, rolling thunder of those 18 cylinders filled the air. Brenner closed his eyes, letting the sound wash over him. He thought back to the cold hangar in Germany where he had first heard that sound in 1944. Back then, it had been a sound of defeat, a reminder of his enemy's power. Now it was simply beautiful. It was the sound of engineering perfection, of a machine built with purpose and humanity. He smiled faintly and whispered, "You taught us well." The P-47's propeller blurred into motion, and for a few moments the old engineer felt young again. The roar of the R-2800 was no longer the heartbeat of war. It was the heartbeat of history. As the R-2800 roared across that English airfield, Brenner realized that his life had come full circle. The same sound that once symbolized fear now embodied something entirely different: admiration, reconciliation, and respect. Around him, spectators cheered as the Thunderbolt lifted gracefully into the sky, its wings glinting in the sunlight. The aircraft climbed higher and higher, leaving behind a trail of smoke that shimmered in the afternoon air. For Brenner, it wasn't just an airplane anymore. It was a testament to what humanity could achieve when imagination met discipline and when power was tempered by purpose. He remembered how, in the closing months of the war, he had stood in the ruins of a factory, surrounded by broken lathes and twisted steel. The bombing had silenced the machines that once defined German pride. In those moments, he had wondered if engineering itself had died with the war. But now, as he watched the P-47 fly overhead, he realized that engineering had never been the enemy. It had always been the hope. Machines like this were proof that progress could be reclaimed, that technology could serve peace as faithfully as it once served destruction. After the flight, Brenner spoke with the restoration team. They were a mix of young enthusiasts and aging veterans, all united by love for the aircraft. When they learned who he was and what he had done during the war, they listened with fascination. He told them how he and his team had examined the captured engine piece by piece, trying to understand its secrets. They expected to hear about espionage and rivalry, but instead he spoke of respect and enlightenment. "We learned from your engine," he told them softly. "We learned what it means to build something for endurance, not for glory." One of the young restorers asked him whether the Germans could ever have built an engine like it if they had started earlier. Brenner smiled. "Perhaps," he said, but not in the same way. We built things to prove we could. They built things to make sure they worked. It was a simple statement, but it carried the weight of everything he had come to understand. The difference between brilliance and practicality, between ambition and execution, was the difference between triumph and failure. Over the years, Brenner's reflections were published in technical journals, though rarely under his full name. He wrote essays about standardization, process engineering, and the importance of interdisciplinary design. Many of his ideas found their way into post-war European industrial reforms. He argued that the age of the lone genius was over, that the future belonged to teams, systems, and collaboration. The R-2800 had taught him that the true strength of engineering lay not in isolated brilliance, but in coordinated effort. In one essay, he wrote, "The most powerful engine in the world is not made of pistons and valves. It is made of people, each performing a small part with precision and pride." That sentence would later be quoted by engineering students for decades to come, inscribed on classroom walls and printed in textbooks. Brenner had distilled the lesson of the P-47 into a universal truth. But before he became a teacher and mentor, there had been those difficult years of rebuilding. Post-war Germany was a landscape of ruins. The Allied occupation imposed restrictions on aircraft design, forcing many engineers to turn to civilian industries, automobiles, tools, and industrial equipment. Brenner adapted, applying his knowledge of aviation materials to manufacturing machinery. He often told colleagues that designing a car engine or a power turbine was no less noble than designing a fighter engine. Each is an answer to a need, he would say. The only difference is what you intend it for. Even as he built a new life, the memory of the R-2800 never left him. He could recall its scent, the faint tang of aviation fuel and oil, the texture of its finely machined parts, the way it vibrated like a living creature when it came to life. Sometimes he would close his eyes and imagine standing once more in that cold hangar, listening to its rhythmic thunder. But instead of the shame he had once felt, he now felt gratitude. That engine had changed him, reshaped his understanding of what true engineering mastery meant. When he corresponded with his former wartime colleagues, many of whom had also found work abroad, the topic often turned to that captured P-47. They all remembered it vividly. One of them, Adler, who had become a professor of metallurgy in Switzerland, wrote to Brenner, "It was not defeat we saw that day. It was instruction. That machine taught us humility. Without it, we might never have learned how to build again." Brenner reread that line many times over the years. He understood that humility was the foundation of progress. Only by acknowledging another's excellence could one truly aspire to surpass it. In the 1950s, Brenner visited the United States for a conference on turbine research. It was his first time on American soil. When he stepped off the plane, he was struck by the sheer scale of everything: the highways, the factories, the energy of a nation still expanding. During the conference, he toured an engine plant in Connecticut where Pratt Whitney continued to produce advanced engines, both piston and jet. As he walked through the immaculate assembly lines, he was overcome by déjà vu. The precision, the discipline, the confidence. It was all there, magnified. The plant manager, unaware of Brenner's past, proudly showed him a newly built R-2800 polished and ready for shipment. Brenner stood before it in silence, tracing its familiar curves with his eyes. The manager, noticing his expression, smiled and said, "They don't make them like this anymore. These are the last of their kind." Brenner nodded slowly. "Then treat it with respect," he said quietly. "It represents the best of what men can do when they build not just for war, but for endurance." After the tour, Brenner was invited to speak briefly to the plant's engineers. Standing before them, he spoke without notes. "You must never think of machines as mere tools," he said. "They are reflections of our values. The way we build shows who we are. I once studied one of your engines under very different circumstances. I thought I was studying my enemy. Instead, I was learning from my teacher." The room fell silent, and then slowly applause began to fill the hall. That moment, more than any other, felt to him like the closing of a circle. The war that had divided nations had, through the strange medium of engineering, also united them. The R-2800 had been a weapon once, but it had become something greater, a shared benchmark for excellence. Its lessons transcended the flags painted on its cowling. It belonged to everyone who believed that progress could be forged not through dominance, but through understanding. Later that evening, Brenner stood outside the hotel, watching the factory lights in the distance. The rhythmic glow of the furnaces reminded him of the endless hum of production that had so amazed him decades before. He realized that the secret he had sought in that captured engine so long ago was never hidden in its metal or design. It had always been in the people who built it, ordinary men and women who believed that good work, done well, could change the world. He smiled at the thought. Then, in the still night air, he whispered the words he had once written in his report. "Exceeds our capability." But this time, it wasn't a statement of defeat. It was a statement of admiration. Brenner's time in America left a lasting impression on him. He returned to Europe with a renewed sense of purpose, carrying with him not only technical insights but also a philosophy that would guide the rest of his career. He began to advocate for what he called cooperative engineering, a model that emphasized collaboration between design, production, and testing teams, inspired directly by what he had witnessed in the American aircraft industry. His colleagues often remarked that Brenner's ideas felt ahead of their time, a blueprint for the kind of integrated design processes that would become standard decades later. In lectures and papers, he used the R-2800 as his favorite case study. He described it not as an exceptional creation, but as an inevitable one, the result of aligning every part of a system toward a single goal. If you design one perfect part, he would say, you build an artifact. If you design 1,000 good parts that work together, you build an engine. And if you can build 10,000 of them exactly the same, you build a civilization. Those words resonated with young engineers who were growing up in a new world defined not by conquest but by cooperation. During the 1960s, Brenner was invited to join a European aerospace consortium developing a new generation of turboprop and jet engines. His experience with materials science and production coordination made him invaluable. Though the technology had changed drastically since the piston era, his lessons from the R-2800 remained relevant. A good engine, he told his new team, must be honest. Every part should tell the truth about what it does. By this, he meant that no component should exist for appearance or prestige. It should serve a clear purpose, and it should do so reliably. His colleagues sometimes joked that Brenner treated engines as if they were moral beings, capable of integrity or deceit. He would laugh and reply, "They are. A dishonest engine will betray you." He kept a photograph of the captured P-47 on his office wall. It was a grainy black and white image taken during the war, showing the aircraft with its engine cowling removed, surrounded by German mechanics in dark overalls. Whenever a young engineer asked about it, Brenner would tell the story again, not as a tale of defeat, but as a parable about discovery. "We thought we were dissecting a machine," he would say. "In truth, we were dissecting our assumptions." As the years passed, the world changed. Jet engines replaced pistons, space exploration replaced dogfights, and the industrial systems that once built weapons began producing consumer goods, communication satellites, and scientific instruments. But for Brenner, the lessons of that wartime encounter never faded. He saw echoes of the R-2800's philosophy in every reliable machine, the emphasis on redundancy, accessibility, and ease of maintenance. These traits, he argued, were not luxuries, but moral imperatives. To make something dependable, he wrote in one of his final essays, is to show respect for those who must depend on it. In the late 1970s, Brenner was invited to the United States once more, this time to attend a symposium marking the 40th anniversary of the P-47 Thunderbolt. Veterans, engineers, and historians gathered to celebrate the aircraft and its impact on aviation history. Brenner, now an elderly man with silver hair and a gentle manner, was introduced quietly as a former German engineer who studied the Thunderbolt during the war. There was a murmur of surprise and curiosity, but when he took the podium, the room fell silent. "I saw this aircraft for the first time when it fell into our hands," he began. "At that time, I was a young man, proud and sure that our engineering was unmatched. Then we opened its cowling and found something extraordinary, not just power, but simplicity, not just precision, but purpose. It was an engine that did not boast. It simply worked." He paused, glancing around the room filled with former pilots and mechanics, men who had trusted that engine with their lives. "We did not hate it," he said quietly. "We respected it, and we learned from it." The veterans applauded him warmly. Some approached afterward to shake his hand, thanking him for his honesty. One of them, an elderly American pilot who had flown P-47s over Germany, told him, That engine saved my life more times than I can count." Brenner smiled softly and replied, "Then it achieved what every engineer hopes for, to protect life rather than take it." That evening, as the sun set outside the hangar where several restored Thunderbolts stood gleaming, Brenner walked slowly among them. He touched the metal skin of one aircraft, feeling the faint vibrations as its engine idled nearby. The smell of oil and fuel brought back decades of memories. He could almost see his younger self, tired, curious, and humbled, standing over that same engine so many years before. The past and present seemed to merge, connected by the enduring heartbeat of the R-2800. Later, one of the event organizers presented him with a small gift, a polished piston head salvaged from a decommissioned R-2800 engine. It was mounted on a wooden base with an inscription, "In recognition of those who studied, learned, and built." Brenner accepted it with trembling hands. "It's beautiful," he whispered. "It's the most honest piece of metal I've ever seen." He kept it on his desk for the rest of his life. In his final years, Brenner often said that the R-2800 had taught him the greatest engineering lesson of all, humility before the machine. He believed that every invention carried the responsibility of its maker, that every bolt tightened was a promise to whoever would use it. To him, the Thunderbolt's engine represented the fulfillment of that promise on a global scale. It was built not to impress, but to endure, and in doing so, it outlasted the very war that created it. When Brenner passed away in 1982, his students and colleagues held a small memorial at his university. On his desk, beside the piston from the R-2800, they found his last handwritten note. It read, "True strength in engineering lies not in surpassing others, but in learning from them." The R-2800 was not our enemy, it was our teacher. That sentence would later be quoted in books and lectures around the world. It summed up the entire story in 12 words, a tale of discovery born from conflict, of respect born from defeat, of knowledge transcending borders. And somewhere, in museums and on airfields across the world, the roar of the R-2800 continues. No longer a sound of war, but a living echo of human ingenuity, reminding everyone who hears it that even in our darkest moments, creation can outshine destruction. Long after Brenner's death, his writings continued to circulate among engineers, historians, and aviation enthusiasts. His essays, particularly the ones about the P-47 and its engine, were translated into several languages and included in engineering ethics courses. Professors would read excerpts aloud to their students, emphasizing his belief that humility and collaboration were as essential to progress as intelligence. The story of a wartime engineer who learned from his enemy became a parable of reconciliation and intellectual honesty. Among the young engineers who studied his writings was a generation that had grown up in a world of computers, satellites, and jet propulsion, technologies far beyond the piston age. Yet even they found inspiration in the lessons of the R-2800. The engine's legacy had outlived its era, not because of its horsepower, but because of the ideals it embodied. In every well-designed system, be it an aircraft, a computer chip, or a power grid, there echoed the same principles: reliability, integration, and respect for the user. In 1990, nearly half a century after the end of the war, a museum in Germany dedicated a new exhibit to engines of the air war. Among the artifacts displayed was a restored R-2800, its polished cylinders gleaming under soft lights. The curators placed a plaque beside it with a quote from Brenner's 1944 report, "Exceeds our capability under current conditions." Beneath that, they added his later reflection, "But not beyond our ability to learn." Visitors who read those words often paused, sensing the quiet journey they represented, from rivalry to respect, from destruction to understanding. The exhibit included photographs of German engineers standing around the captured P-47 during the war. Their faces, once stern and analytical, now looked strangely humanized in the passage of time. Some visitors recognized their names from history books, others from universities. The display didn't glorify or condemn, it simply told the truth, that even in the midst of war, knowledge had crossed enemy lines and planted seeds for a better future. One corner of the exhibit featured a small glass case containing Brenner's personal effects, his fountain pen, a slide rule, and a faded photograph of the P-47's engine bay. Next to it sat the very piston that had been gifted to him at the Thunderbolt anniversary decades earlier. Its surface had dulled with age, but its form was as perfect as ever. Beneath it, a simple inscription read, "To those who listen, when machines speak." Visitors often remarked on how the display managed to convey both the grandeur of industrial achievement and the fragility of human ambition. The R-2800 stood there, not as a relic of war, but as a monument to cooperation. The museum guide would tell Brenner's story to each new group, how he had once examined this engine as an enemy and how it had changed him forever. Many left with a sense of quiet awe, realizing that even in times of chaos, the pursuit of understanding could bridge worlds. Across the Atlantic, the P-47 Thunderbolt itself remained a beloved icon of aviation history. Restorers continued to keep several of them flying, their R-2800s maintained with the same care and reverence that Brenner had once described. At air shows, the crowd would fall silent as the aircraft taxied out, then erupt in cheers when the engine thundered to life. The deep, rhythmic rumble carried something more than nostalgia. It carried history. Pilots often said that when they flew a Thunderbolt, they felt connected not just to the past, but to every engineer and mechanic who had made it possible. In one such air show in 2005, a veteran pilot named Thomas Green gave a brief speech before taking off in his restored P-47. "This plane," he said, tapping the cowling, "was built by Americans, studied by Germans, and admired by everyone who's ever loved flight. If that's not proof that machines can unite us, I don't know what is." When the propeller spun and the R-2800 began its familiar growl, the crowd stood in reverent silence, the sound resonating deep in their chests. Among the spectators that day was a young German engineer named Lucas Adler, a distant relative of the metallurgist who had worked with Brenner during the war. He had read Brenner's writings and considered them a personal inspiration. As the P-47 climbed into the sky, Lucas felt tears sting his eyes. He wasn't thinking of nations or history. He was thinking of the engineers, men like his great-uncle and Brenner, who had turned even their defeat into a lesson that shaped the future. When the plane passed overhead, sunlight flashing off its wings, he whispered, "You were right. We did learn." Later, Lucas would go on to work in aerospace materials research, specializing in high-temperature alloys for jet turbines. In interviews, he often credited his fascination to an old report my family kept from the war. He explained that what had begun as a technical document had become a moral guidepost. "Every time I work on a new alloy," he said, "I think of those men who examined an enemy's engine and found inspiration instead of bitterness. That's how progress should work, through respect." Back in the United States, the legacy of the R-2800 endured in more subtle ways. Modern engineers continued to study its design, marveling at its balance of simplicity and performance. The Smithsonian's National Air and Space Museum featured one prominently, describing it as a masterpiece of mass-produced reliability. Visitors could see the intricate network of pipes and cylinders, and many walked away with newfound appreciation for the craftsmanship of the 1940s. One of the museum curators and aviation historian summarized its legacy beautifully. The R-2800 wasn't just a product of American industry, it was a statement of human capacity. It showed that when knowledge, discipline, and cooperation align, the results transcend nationality. That quote was later engraved on a plaque near the display, joining Brenner's words across the ocean. By the early 21st century, only a few operational R-2800 engines remained in the world, lovingly maintained by enthusiasts who understood their significance. Whenever one was started, it drew crowds, not just because of its sound, but because of what it represented. It was the heartbeat of an era that had reshaped the world. In a sense, the story had come full circle once again. The engine that had once terrified German engineers, humbled them, and later inspired their successors, had become a universal symbol of what engineering could achieve when guided by purpose. It was no longer the American engine the Germans couldn't match. It was the human engine everyone could learn from. And in that transformation, from fear to fascination, from rivalry to respect, the R-2800 fulfilled its greatest role. It ceased to be a tool of war and became instead a bridge of understanding, a mechanical reminder that even in humanity's darkest times, our creations can lead us back toward the light. By the time the 21st century was well underway, the story of the German engineers who had examined the captured P-47 had become more than a historical curiosity. It was a study in the human side of engineering. Documentaries, books, and museum exhibits began to tell their story not as that of defeated enemies, but as of men who recognized greatness when they saw it. It fascinated people that, amid one of the most destructive wars in history, there could exist such an instance of quiet respect, of minds reaching across the divide of conflict to acknowledge excellence. Historians who studied the wartime archives often remarked on how strikingly honest the German reports were. They were written in precise technical language, but the undertones of admiration were clear. One researcher noted, "You can almost hear the sighs between the lines." When comparing the R-2800 to engines like the BMW 801 or Daimler-Benz DB603, the Germans didn't mask their conclusions with propaganda. They stated plainly that the American engine was superior in endurance, simplicity, and manufacturability. It was one of those rare moments when professionalism triumphed over ideology. Academic institutions began using the P-47 story in leadership and engineering courses. Professors used it to illustrate how humility in the face of another's innovation can lead to true progress. These men could have dismissed what they saw, one lecturer explained. Instead, they chose to learn from it. That decision, quiet, technical, and entirely human, helped shape post-war engineering in Europe. The students who listened were often amazed that such a profound lesson could emerge from something as mechanical as an engine inspection. Yet it was precisely that, the merging of human character and machinery, that made the story timeless. At one such university in Munich, a bronze replica of a single R-2800 cylinder was displayed in the engineering faculty's atrium. A small plaque beneath it bore Brenner's quote, "The true secret of that engine was not in its metal, but in its method." Every year, new students would pass by it, many unaware of the full story behind the words. But for those who did know, it served as a reminder that greatness in engineering is not about imitation. It's about understanding why something works and how it fits into a larger system. Meanwhile, surviving wartime documents continued to reveal fascinating details. One declassified report included a line handwritten in the margin by one of Brenner's assistants. "No miracle here, only mastery." That phrase perfectly captured what they had discovered. The R-2800 wasn't the result of secret technology or alien genius. It was the outcome of discipline, organization, and teamwork. It was proof that true innovation is often built not on flashes of brilliance, but on consistency and structure. In the years that followed, aviation enthusiasts continued to gather at air shows around the world, celebrating the aircraft that carried the R-2800, the P-47, the F-6F Hellcat, the F-4U Corsair, and others. Each represented a different expression of the same engineering philosophy. The Thunderbolt, though bulky and inelegant by some standards, remained a favorite because it embodied everything Brenner had admired: strength, resilience, and dependability. Pilots often joked that it could take off with half its parts shot away and still find a way home. That reputation wasn't exaggeration. It was testament to the engine that powered it. At one commemorative event in Normandy marking the 80th anniversary of D-Day, an old Thunderbolt performed a low pass over the beaches where so many had once fought and died. The deep growl of its R-2800 echoed across the cliffs, and for a moment, time seemed to stand still. Veterans, families, and tourists looked skyward as that sound filled the air, a sound that once symbolized destruction but now carried something different: remembrance and respect. An announcer spoke over the loudspeaker, recounting how German engineers had once studied this very engine and admitted, with professional honesty, that they could not match it. The crowd applauded not out of nationalism, but out of awe for human ingenuity itself. After the flight, a small group gathered around a temporary display that told Brenner's story. Among them was a German woman in her 70s who introduced herself quietly as Brenner's granddaughter. She carried with her a leather-bound notebook, carefully preserved, filled with sketches, calculations, and notes written in her grandfather's neat hand. She explained that it contained his reflections on the R-2800 and his later thoughts on engineering ethics. "He always said that engine changed him," she told the crowd. "He used to say it reminded him that engineering should serve life, not destroy it." Her words moved the listeners deeply. One American mechanic who had spent decades restoring vintage warbirds stepped forward and shook her hand. "Your grandfather's story," he said, "is why we keep these planes flying. It's not just history, it's heritage." She smiled and nodded, saying softly, "That's exactly what he would have wanted." Later that evening, as the sun dipped below the horizon, she stood alone by the Thunderbolt, listening as its engine cooled and ticked quietly in the dusk. The metal still radiated warmth from its flight. She placed her hand gently on the cowling, just as her grandfather once had, and whispered, "Danke." In that small gesture, the touch of one generation thanking another, the story reached its quiet, poetic conclusion. The R-2800 had outlived its builders, its pilots, and its enemies. It had transcended the very war that created it. What began as an instrument of battle had become a symbol of reconciliation, a testament to what humanity can achieve when we seek to understand rather than dominate. When museums, scholars, or pilots tell the story today, they no longer frame it as the German engineers who couldn't match the American engine. Instead, they call it the engine that united its admirers. It stands as proof that excellence, when honestly recognized, belongs to everyone. Whether built in Connecticut or examined in Bavaria, its legacy is shared, a reminder that even amid destruction, curiosity and respect can forge a bridge stronger than any steel. And so, every time a Thunderbolt starts its engine and the R-2800's rolling thunder fills the sky, it carries with it not only the sound of 18 cylinders firing in perfect rhythm, but also the echo of understanding. The voice of men like Brenner, who once took apart an enemy's machine and discovered within its pistons and gears the enduring heartbeat of human progress. In the decades that followed, the legend of the P-47's engine continued to ripple quietly through history, not as a story of rivalry, but as a testament to shared human potential. Aviation historians often remarked that the tale of the German engineers who studied the R-2800 was one of those rare stories where science transcended ideology. It revealed that even in times of hatred and destruction, curiosity and respect could survive. As new generations of engineers took to digital tools and computer-aided design, some of them looked back on the piston age with a kind of reverence. They saw the R-2800 not merely as a machine, but as a symbol of craftsmanship, an artifact from a time when engines were hand-assembled yet produced with mathematical precision. One professor of aeronautics once told his students, "If you want to understand what it means to design something truly great, study the R-2800. It's a conversation between mind and metal." That conversation had begun in the 1940s, in a cold hangar where German engineers had unbolted each component in silence, and somehow it had never ended. Every generation since had added a new verse to it. The R-2800 was now a teaching tool, a symbol, and an inspiration. Museums displayed its cross-sections under glass, restorers tuned its cylinders as if performing a sacred ritual. Its sound, deep, rhythmic, commanding, had become part of aviation's soul. In 2010, a historian named Dr. Elise Kramer published a book titled Engines of Understanding: How the P-47 Taught the World to Listen. The book chronicled Brenner's story in detail, drawing from his surviving letters and interviews with his family. Kramer argued that the captured P-47 incident symbolized the moment when technology ceased to belong to nations and began to belong to humanity. The R-2800, she wrote, did not win the war. It helped win the peace. It inspired those who once opposed it to emulate it, and in doing so, it unified them under the shared language of engineering. The book became surprisingly popular, not just among historians, but among readers who saw in it a broader lesson about humility and collaboration. Schools began assigning excerpts to students in ethics and design programs. Brenner, who had died decades earlier, was now remembered not as an enemy engineer, but as a bridge between worlds. His name appeared in documentaries, often spoken with quiet respect by narrators who described his transformation from rival to admirer. Meanwhile, in the small Bavarian town where Brenner had once lived, a local aviation club restored a P-47 replica. They painted it in the colors of a historical squadron, but added a small, discreet inscription on the side beneath the cockpit, "In memory of those who learned from their enemies." The project brought together volunteers from across Europe and the United States, retirees, students, and mechanics, all working side by side. It took them nearly 5 years to complete, and when the aircraft finally rolled out of the hangar, gleaming in the sunlight, it was as if Brenner's vision had come to life once more. On the day of its first test run, the entire town turned out to watch. When the engine finally coughed, sputtered, and came alive, a deep rumble filled the air. Children covered their ears, elders smiled knowingly, and a few eyes filled with tears. For those who understood the story, that sound wasn't just noise. It was history, breathing again. A former American pilot, now in his 90s, attended the ceremony as an honored guest. Standing beside the mayor and Brenner's granddaughter, he said, "This engine once divided us, but now it brings us together. That's the greatest victory of all." As the propeller spun and the engine settled into its steady rhythm, The crowd applauded, not for the machine itself, but for what it represented. The R-2800 had become something greater than its creators could have imagined. It was no longer a symbol of wartime superiority, but of reconciliation, craftsmanship, and enduring human spirit. Later that evening, as the restored Thunderbolt rested in its hangar, Brenner's granddaughter was invited to speak. She stood before the assembled guests, her voice calm and clear. "My grandfather used to say that machines have souls, not because they think or feel, but because they carry the intentions of the people who build them. When those intentions are good, when they're guided by respect and discipline, then even a weapon can one day become a teacher. That's what this engine became. A teacher." Her words hung in the air for a long moment before the audience erupted into applause. Among those listening was a group of young engineering students from Munich. They had come to witness the event as part of their university project. Afterward, one of them said quietly to his friend, "It's strange, isn't it? We study formulas and materials all day, but this is what engineering really means." His friend nodded. "It's about building something that outlasts hate." That night, after the ceremony, the engine was started one last time under the moonlight. The sound echoed across the fields, a low, steady growl that seemed to blend with the night itself. Brenner's granddaughter stood near the hangar doors, watching as the propeller glinted silver under the floodlights. For her, it was more than a demonstration. It was a conversation between generations, between the past and the present. The same sound her grandfather had once described in his reports now spoke to her in a different way. It was no longer the sound of an enemy's power. It was the voice of redemption. In that moment, she understood why he had devoted his life to teaching others what he had learned from that engine. It wasn't about the horsepower, the metallurgy, or the supercharger. It was about the humility of learning, the courage to admire, and the will to improve. As the R-2800 idled to a stop and the propeller blades slowed to stillness, she felt a deep, quiet peace. The crowd dispersed slowly, but the story did not end there. In the years that followed, that same P-47 replica toured Europe, appearing at air shows and commemorative events. Everywhere it went, it carried Brenner's message with it. Children climbed onto their parents' shoulders to see it. Veterans saluted it. Engineers examined it with reverent curiosity. Each time its engine started, the deep thunder reminded everyone that progress is not born from pride, but from understanding. By the time the aircraft reached its final home, a museum near Munich, it had logged hundreds of demonstration hours and inspired thousands of visitors. Its plaque bore simple words, chosen from Brenner's final note: "True strength in engineering lies not in surpassing others, but in learning from them." Those words, like the steady hum of the R-2800, continued to echo long after the engine fell silent. As the replica Thunderbolt became a fixture in the Munich Museum, its story began to draw visitors from around the world. Aviation enthusiasts came to admire its craftsmanship, while students came to learn about its deeper message. The museum's curators noticed something remarkable. Visitors often lingered longest, not by the aircraft's wings or propeller, but beside the small display that told the story of the German engineers who had examined the original captured P-47. There was something profoundly human about that part of the exhibit, something that reached beyond technical fascination into moral reflection. People stood reading the translated excerpts from Brenner's wartime report and his later writings. His words, once confined to classified documents and dusty archives, now shone beneath the glass case. "It is not brilliance that makes greatness, but discipline." Beside that quote was a photograph of the original team, weary but proud, standing around the dismantled R-2800 in 1944. Their faces, once locked in the intensity of a crumbling war, seemed to hold a quiet dignity. For the museum's visitors, they were no longer the enemy. They were engineers, human beings united by the same hunger to understand. One afternoon, a group of American visitors arrived, veterans' descendants touring Europe. Among them was a man named Jack Harlow, whose grandfather had flown P-47s during the war. When he saw the display, he felt an unexpected tug of emotion. Reading Brenner's account of hearing the R-2800 roar to life during testing, he imagined what it must have been like for those German engineers to stand before that engine, caught between admiration and despair. Harlow turned to the guide and said quietly, My grandfather trusted his life to that engine. It's strange to think the men on the other side respected it too. The guide nodded. Respect, she said, is the foundation of progress. It's the one thing war can't destroy. Moved by the experience, Harlow later wrote a letter to the museum thanking them for the exhibit. I grew up thinking of that engine as a weapon, he wrote. Now I understand it was also a bridge. My grandfather's survival depended on its strength, and their redemption began with understanding it. His letter was later framed and added to the display. It became part of the ongoing dialogue that the R-2800 continued to inspire, a conversation between generations, across languages, across what had once been a battlefield. The replica Thunderbolt itself became a kind of ambassador. The museum staff would start its engine on special occasions, and people from miles around would come just to hear the sound. When it roared to life, echoing through the Bavarian hills, it drew a silence before applause. Some closed their eyes, feeling history vibrate through the air. Others simply smiled. The sound had long since ceased to symbolize war. It was now the sound of connection. The aircraft's caretaker, an aging mechanic named Otto, had dedicated his later years to maintaining the R-2800. He treated it with reverence, often speaking to it as if it were alive. "You've seen everything," he would murmur while checking its oil lines. "Don't let me make you look bad now." Visitors sometimes laughed at his habit, but Otto would simply wink and say, "Respect keeps engines running." When asked why he cared so deeply about an American design, he would shrug. "Engines don't have passports," he'd reply. "They only speak one language: performance." It wasn't only engineers and historians who found meaning in the story. Philosophers and writers began referencing it in essays about ethics, pride, and humility. The image of the German engineers studying an enemy's masterpiece became a metaphor for human learning itself. One author described it as the moment when defeat became education. Another wrote, "The P-47's engine did not only power aircraft, it powered empathy." Those words resonated far beyond the world of aviation. In 2020, a documentary film titled Thunder and Understanding premiered on international television. It told the full story, from the wartime examination of the captured P-47 to the post-war friendship between former adversaries. Using restored footage, letters, and interviews with Brenner's descendants, the film portrayed the R-2800 as both a technological and moral triumph. The director concluded the film with an image of the Munich Thunderbolt starting its engine at dawn, its propeller blurring as the sun rose behind it. Over the sound of the rumbling engine, the narrator read Brenner's final words. "We thought we were studying a machine, but we were studying ourselves." The film struck a chord around the world. Teachers used it in classrooms, engineers quoted it in conferences. Even outside aviation, professionals saw in it a universal truth: that excellence can inspire admiration even among rivals, and that the willingness to learn from others is the essence of progress. Back at the museum, Brenner's granddaughter continued to serve as a volunteer guide. She spoke to students, tourists, and veterans alike, always beginning with the same introduction. "This is not a story about war. It's a story about learning." She often ended her talks by asking visitors to look closely at the R-2800's polished metal and think about all the hands that had touched it. American workers in factories, pilots in combat, German engineers in captured hangars, mechanics in restoration shops, and now the curious children who peered at it with wide eyes. Each of them, she would say, kept it alive in their own way. One day, after finishing her talk, she stood quietly by the display, watching a group of young students take notes. One of them asked her, "Do you think your grandfather forgave himself for building things that were used in war?" She thought for a long moment before answering. "I think he made peace with it," she said softly. He realized that an engineer's duty is not to the war or the weapon, it's to the truth of the machine. And when you serve that truth honestly, it can lead you back to peace. Her answer captured the very spirit that had transformed a captured engine into a lasting lesson. The R-2800 had taught generations that progress wasn't about domination. It was about understanding the systems, both mechanical and human, that make the world work. That evening, when the museum closed and the lights dimmed, the Thunderbolt sat silently beneath its hangar lamps. Dust motes drifted through the air, settling on its wings like fine snow. The great radial engine rested, its once roaring heart now quiet but eternal. It had outlasted the war, outlasted its makers, outlasted even the ideologies that had once divided nations. And though it could no longer fly into battle, it continued to lift minds into understanding. Outside, the wind swept through the trees, carrying a faint echo of its sound, a phantom vibration that seemed to whisper what Brenner himself had written so long ago. True strength lies not in surpassing others, but in learning from them. Years passed, and the museum's Thunderbolt became something of a pilgrimage site for engineers, aviators, and dreamers from every corner of the world. Each year, on the anniversary of the P-47's first flight, the museum held a special ceremony. They would start the R-2800 one more time, letting its mighty voice roll across the airfield. Visitors described it as a sound that seemed to come not from metal and fuel, but from memory itself, a deep, resonant pulse that connected generations. Among those who attended one such ceremony was a young aerospace engineer named Daniel Fisher. He had traveled from America to see the aircraft his grandfather had once helped maintain during the war. His grandfather, an aircraft mechanic in the U.S. Army Air Forces, had spoken of the R-2800 with a kind of reverence usually reserved for living beings. That engine, he used to say, wasn't just built, it was born. Daniel had grown up hearing those stories, but standing there in front of the gleaming Thunderbolt, he finally understood them. The engine's massive cylinders and thick pipes didn't just represent machinery. They represented trust. Trust between pilot and mechanic, between engineer and craftsman, between nations divided by war but united by curiosity. As the engine started up and the air trembled, Daniel closed his eyes. For a moment, he could almost hear his grandfather's laughter in the rhythm of those 18 pistons. After the ceremony, Daniel met Brenner's granddaughter, who was now elderly but still full of energy. They talked for a long time about their grandfathers, men who had lived on opposite sides of history, but had ended up sharing the same reverence for what they built. Maybe, Daniel said with a smile, that's how peace really happens. Not through treaties, but through understanding. She nodded. Yes, she replied, through the hands that build and the minds that learn. That night, the two of them walked together through the quiet hangar after closing hours. The Thunderbolt rested in the shadows, its silver skin glowing faintly in the dim light. Daniel ran his fingers over the cowling, feeling the cold, smooth metal. Do you think, he asked, if the men who fought the war could see this, see people from both sides here together, they'd be proud? I think they'd be relieved, she said softly, because it means all that work, all that suffering, became something good in the end. They stood there for a while, listening to the soft ticking of the engine as it cooled, a sound like the heartbeat of time itself. Then she said something that Daniel would never forget. My grandfather once told me that engines are honest mirrors. They show us what kind of people we are. This one, she said, gently tapping the cowling, showed us that we could learn to respect even our enemies. And that might be the most important lesson any machine has ever taught. The following morning, Daniel boarded a flight home. As the aircraft climbed into the clouds, he looked out the window and thought about what he'd seen. The jet engines outside hummed smoothly, the descendants of machines like the R-2800. He imagined Brenner's team examining that old engine decades ago, writing their notes by lamplight, realizing they were staring at the future. Now that future had arrived, and it was peaceful. He whispered a quiet thank you, not to any nation, but to the spirit of creation that had made such things possible. Back at the museum, life went on. New visitors arrived every day, each finding something different in the story. Some saw the P-47 as a symbol of victory, others as a symbol of cooperation. For engineers, it was a masterclass in design. For philosophers, it was a study in humility. For children, it was simply a big, beautiful machine that could fly. And for those who knew the full story, it was all of those things at once. A single engine that had carried humanity through destruction and somehow emerged as a lesson in peace. The museum's staff made sure that Brenner's story never faded. They digitized his reports, letters, and post-war essays, creating an online archive accessible to anyone who wanted to learn. People from around the world began reading his words. Victory belongs not to the nation that invents most brilliantly, but to the one that learns most honestly. His philosophy resonated deeply in a world where collaboration across borders had become the key to every major technological breakthrough, from clean energy to space exploration. One day, a student left a note in the museum's guestbook. It read, "I came here to see an airplane, but I'm leaving with a lesson about people." That single line summed up what the entire exhibit stood for. The story of the captured P-47 and its 2,000 horsepower engine wasn't about machines defeating machines. It was about people discovering that respect could travel farther than rivalry. As decades turned into centuries, the R-2800's roar became rarer, but recordings of it continued to echo in documentaries, museums, and archives. Even as aviation moved into the realm of silent electric propulsion and whispering ion thrusters, the old recordings of that engine's thunder still stirred something deep within the human heart. It reminded people that there had been a time when machines were loud and raw and alive, and that even in their noise they carried wisdom. Future historians would look back on that wartime encounter between the German engineers and the captured P-47 as more than a technical footnote. They would see it as a pivotal moment when human curiosity triumphed over pride. The Germans had not been able to match the R-2800, but in admitting that, they had taken the first step toward matching its spirit. The lesson had echoed through generations. True advancement comes not from denial, but from acknowledgement. In the museum, as night fell and the last visitors left, the lights dimmed over the Thunderbolt. The aircraft seemed almost to rest, its polished surface reflecting the faint stars through the hangar windows. Somewhere in the silence, the memory of its engine seemed to hum faintly, as if whispering a final truth. The whisper said that humanity's greatest inventions are not weapons or engines, but understandings, the moments when knowledge passes from one hand to another, undiminished by borders or time. That was the true legacy of the R-2800, not the horsepower it produced, but the respect it inspired. And so, even as the years carried its sound farther into memory, its story continued to live, carried by engineers, pilots, dreamers, and anyone who believed that learning from one another was the most powerful force ever built. Somewhere, perhaps, a new engineer reading Brenner's old report would come across his closing line and smile. It would read, "The machine before us is magnificent, but what is truly magnificent is that we can recognize it as such. That is what makes us human." And with that final thought, the story of the P-47's 2,000 horsepower engine, once examined in awe by its enemies, finds its peace, its purpose, and its immortality.